Cloud. Okay, awesome. Let's start. So today we're going to talk about quantum mechanics, which is a pretty cool topic. It definitely is one of the cooler topics in physics. And I think in this lecture, there's going to be a lot of times where I'm going to ask a lot of questions because quantum mechanics really asks you to reflect on your own intuition about how the world works. So I really hope y'all can participate a lot and feel free to just come in with questions because I suspect there will be a lot of questions. So let's dive in. So we're going to start off with a little bit of history, specifically going back to Young's double slit experiment. And this was done in 1801. And this was done with light actually, but we're going to first talk about it with particles. And so what this experiment was you had a wall with two slits in them, and what Young did was he shined light through this through these slits, and there was a screen at the other end, so he would see what kind of patterns were like on the other side. But when we start off with particles, what do you guys think the distribution on the other side is going to be if we have the slits far apart from each other and also close to each other? First question. If people could just shout it out and or write in the chat. So if we had slits far apart and close together, what kind of distribution? And this is with like bullets, so not with light. We're starting with particles first. So somebody said radial ripples with interference. Oh, whoops. Okay, what do I mean by distribution? So essentially, like if I'm thinking of this in terms of bullets, like bullets are going to like pierce, like if I had a piece of paper on the other side, like they would like make holes, right? So like what would be the general concentration of holes on the paper? Would they just like be evenly spread out? Would there just be like an even spread, random spread of like holes, or would there be some certain like pattern or concentration of holes that I can see? Okay, so people said concentrated into bands. I'm assuming that's like the two bands of the slits. Also keep in mind that this is like a spray, so they're not like they're not being shot perpendicular to the wall, so they're kind of at all angles. Somebody said intervals.
What does it even mean? Why would I say that? She's gonna roast me.
Oh, what? No, I'm not gonna roast you. No. Oh, no. Wait, what do you mean by intervals though? Like, okay, maybe. So I guess the general gist of what I'm getting is there's going to be some kind of band structure that's going to happen. Lol. Okay, please don't feel bad. I'm not going to roast anybody. All I do, like everybody is going to have right or wrong answers, and I mean nobody on their day-to-day thinks about these kind of stuff, so I don't really expect you to
Yonna,
understand.
did you get Claire's question?
Oh yeah, the distribution.
Uh-huh.
Yeah, I did.
Okay.
I mean, that was kind of me explaining in terms of like the bullets and the holes. But I guess, okay, this is so if the slits are far apart, then essentially what we'll get this kind of distribution where you'll kind of have a concentration of holes around one of the slits and another on the other slit. And you might get, because of the spray, you might get some kind of some holes like around it, but generally you'll kind of get this bell curve, and you'll get kind of two generally distinct bell curves. And when they're really close to each other, you're going to get something like this, where because they're so close together, you might as well maybe consider it even as one hole, and you'll kind of have a combined distribution. And so hopefully this makes sense. I think maybe the question was kind of confusing, or like it wasn't really clear what kind of answer I was looking for, but hopefully this makes sense. If you think about it just in terms of particles and two slits. And so what Young did was he did this with light. And what he did was he also did it, like if you do it with slits far apart, you'll get something similar to what we saw with the bullets, in that you'll get kind of two distinct distributions. But the closer you brought the slits together, all of a sudden you would see this band structure here. And what this is kind of due to an intrinsic property of waves, which is diffraction and interference. And so what's happening here is that waves bend around an obstacle. This is what diffraction is. And so kind of like what we saw here in this kind of, in this GIF, can you guys see my mouse? Yes?
Yeah.
Okay, cool. So one thing that you can see here is that like the waves are hitting the other side of the wall. And like clearly that would never happen with a particle. A particle would never just like bend around and hit, but waves do that. That's just a natural property of waves. So that's diffraction. And also because we have these two slits, we essentially have these two kind of points where these waves are propagating, like right here and right here. And the 2 points will then produce waves that constructively and deconstructively interfere with each other. And what that means is, just one moment. And what that means is right here, you can see the kind of top points of the waves. When they add up, they'll kind of add up to become like a bigger wave. And when the waves are kind of out of sync with each other, so the tops correspond to the bottoms, they'll kind of cancel each other out. And crests are just the names for the top, and troughs are the names for the bottom. So you'll kind of get this altering kind of pattern of constructive and deconstructive interference. And so what you can kind of see here is that here you kind of have a point of deconstructive interference, and then here you'll have a point of constructive interference. So it's especially kind of strong. And here's kind of a real life example of what you can see of this result using like a green laser. And so this kind of was really incriminating evidence that light was a wave. However, okay, sorry, this is being weird. Okay. So light is a wave, right? For about more than 100 years, that was pretty much the expected or the accepted model for light. However, it quickly came to a realization that this might not be the exact picture, and that was because of something called the photoelectric effect. So what the photoelectric effect is this effect observed when you shine light on a piece of metal, and what that would do is it would release electrons. And so using the kind of classical theory of waves for light, this would imply that if you increase the intensity of light, so if you made the light even brighter, then what would happen is that you would be increasing the power of the wave. So that means when the light is hitting the electrons on the surface of the metal, it would kind of impart more kinetic energy to these electrons. And so they would be flying out faster. And also it was kind of predicted that, well, if we kind of change the frequency of our light wave, so frequency is kind of like how squished together the waves are. If it's more squished together, then that must mean that there's kind of like, I kind of like to think of it as like, there's more of a wave to kind of kick more electrons off of the surface. So you kind of get an increased number of electrons being released. And there was also this kind of predicted time lag, which was kind of in the sense that if you had, let's say like a not so intense beam of light, there would kind of be this time lag between kind of continuous waves hitting the surface of the metal for it to then kind of kick light or kick electrons off of the surface. So that's kind of the predicted theory from kind of our understanding of light as a wave. However, does anybody kind of have an idea of what would happen, or like, do you think that's going to be the correct like, or is that what you think we're going to see when we actually do the experiment with the photoelectric effect? Up to this point, everybody's kind of accepted that light was a wave. So there's no reason for us to kind of think that light was not a wave, and therefore it wouldn't follow this classical theory of waves, right? However, it was observed that this was not the case at all, and that if we shined super bright, so super intense red light onto a piece of metal, no electrons would be observed at all. And just a reminder, red is a low frequency color, while something like blue is a high frequency color. However, if we shined really faint but really blue light onto a piece of metal, the electrons would have a really fast velocity. So the observed relationship was that intensity was actually a measure of the number of electrons, while the frequency was actually a measure of kind of the kinetic energy or velocity of the electrons imparted. And in fact, with all ranges of intensity and frequency, there was no time lag observed. And so, you know, people were really stumped because this kind of meant that somehow light was not acting like it should if it was supposed to be a wave. And so the photoelectric effect was then explained by Einstein, I think in like 1905 or like early 1900s. And this is actually the work that got him his Nobel Prize.
I want to point something out as well. So one of the weird things that you observe is that if you take like redder light and you shine it on a metal, it doesn't really matter how bright it is. It actually doesn't create any electrons at all.
Yeah.
But if you have even really, really faint, like bluer light, even if it's like super, super faint, it still releases electrons.
Yeah.
That's a big part of it as well.
Yeah. And so what's happening here is that, so this was Einstein's kind of theory, and he said that, okay, well, classical wave theory is not giving us any kind of theoretical explanation for what's going on. But if you think of light as a particle instead, this actually gives us the answer. And what he said was that photons have a discrete amount of energy, which is proportional to its frequency. And so this relationship is given by E equals h nu. And so E is the energy, h is a constant, which is actually really tiny. It's 10 to the negative 34. So it's a very small constant. And nu is frequency of the light. And so through this effect, or through this kind of theory, Einstein was able to kind of properly explain what was going on, what was observed through the photoelectric effect. And I mentioned earlier how there's like red light, how with red light there was no observed electrons, but with blue light there was kind of observed electrons regardless of the intensity of blue light. And if you kind of explore the range of frequencies, there is a threshold frequency or like a minimum frequency that will produce electrons. And the energy related to this minimum frequency is called the work function. And so here you can see in this equation, you have the energy of the photon is kind of divided into two parts. One, which is the work function, which I like to kind of think of as the minimum energy required to like even start kicking electrons off of the surface of the metal. And then the rest of the energy of the electron is then imparted into the, the rest of the energy of the photon is then given to the electron to then kind of like give its the kinetic energy for it to kind of fly away off of the surface. So I've just kind of, I haven't really addressed the fact that all of a sudden now we have these two very separate kind of theories for light, like kind of this theory of light as a wave and light as a particle. And so we have very strong evidence from Young's double slit experiment that light is a wave, and through the photoelectric effect, we now have really strong evidence that light is a particle. So what's going on? Is light a wave or is it a particle? And so scientists thought, okay, why don't we then revisit the double slit experiment, but now do it with kind of this new idea and this new concept of light as a photon. And so what scientists did is they were able to create a light source which was dim enough to essentially be shooting out one photon at a time. And what they did was kind of similar to what we did with the bullet kind of experiment at the beginning. They essentially shot out one photon at a time through one or two of these, or one of these like double slits. And so they kind of did it in a range. So they didn't necessarily pick which one. And they, on the other side, they had a detector. So it showed which, like where the photon was hitting. And so here you can see, it seems pretty random. that's like the bullet where we just have kind of two even distributions, or do you
Sorry,
think we'll
Yonna,
see
the
something
audio
different?
cut out for the past like 30 seconds-ish.
Oh, okay.
Could you go over that again?
Sure.
So at first it starts off random. That's where you were.
Sorry, say that again.
You were saying that it starts off looking random and then it cut out.
Oh, okay. Sorry about that. So what I was saying was, okay, so it started out random. I was asking, what do you guys think? Like, please, like, leave down a comment or say out loud what you think the pattern will be. So what we're doing is we're sending in one photon at a time. What do you think? Well, do you think we're going to have a pattern like the bullet where we have like two even distributions, or like one kind of global bell curve, or do you think we're going to see kind of these bands like we saw with like the waves? So do you think we'll see a particle pattern or a wave pattern, essentially, is what I'm asking. Okay, one person said wave pattern.
So some food for thought is like, you might think that like the photons will interact with each other, and act like and that will make it look like a wave. But because we're sending in one photon at a time, like there's only one photon, like so like there's no other photon for it to interact with. Like that's like why we're doing the experiment, to see what would happen.
Yeah, I was describing how earlier with the waves, there were kind of like two sources of the waves because it was a double slit. So in that sense, it could like interfere with it, with the kind of other waves. Somebody said normal distribution. I'm assuming they're, I don't know if by normal they mean like a particle or like a wave. Whichever is right. Okay. What do people think? I think this is like really interesting. So, I mean, a photon is still light. So in that sense, you might think that it will kind of produce the wave pattern like we saw with light when we just kind of when we shined it like a normal like light beam. But it's also just like one photon at a time. So maybe it is like a particle. Okay, I guess is it that people don't want to answer, or are they still confused what's going on? Or something else? Big confused. Okay. What are you confused about? Which part? Both. Okay.
So I guess the idea is like when you do the normal double slit experiment, you're sending in a whole lot of light all at once. And so like that behaves as a wave. But it turns out that you can actually show that like light is actually like if you shine like very low intensity light, that it like lands in very well-defined spots. Like it's like there's such a thing as like a light particle. And so the question is, if you make your light really, really, really dim and you shine it and you do the double slit experiment, but you shine like really dim light so that there's only like one photon at a time, like will it still look like a wave pattern? Because like it's like single particle, so it sounds like it would be like bullets. And so like because there's only one photon at a time, like they're not like interacting with each other. So like
yeah, somebody asked in the chat whether or not the photon would diffract, and it won't because it's a particle. So yeah, maybe just to clarify, when I was talking about diffraction and kind of interference, those are key properties of waves. So like I said, how like a bullet won't just suddenly kind of bend around, right? So it won't, that's like particles don't diffract, but waves do. So hopefully that kind of helps
Yonna,
explain.
if I can quickly jump in and maybe review something from E&M that might help people understand this better.
Okay.
If you're thinking about light as a wave, what does the brightness of the light correspond to about the wave? This is
Wait.
from Astro and E&M as well. It's relevant to both. Can you write that down in the chat?
Oh, me? Wait, sorry.
No, sorry, no. The
Oh,
class.
okay. This is a good review because these are pretty fundamental.
So
Oh,
the question is, if you're thinking about light as a wave, what does the brightness of the light correspond to? Like, how does the wave look if you increase or reduce the brightness of the light? How will the wave change? Brightness is amplitude. That's right. So, so if we're looking at light purely as a wave, reducing the brightness would be reducing the amplitude of the light wave. However, if you're looking at light as a particle, the equivalent would be the number of particles, right? So essentially, if you're talking about like thousands and thousands of light particles, you can just look at amplitude of the light wave as like a continuous number that can change as much as you like. But as you get down to, again, you might remember this from thermodynamics. I mentioned the quantization. As you get to really, really low amplitudes, you start noticing that the light is quantized. You can't reduce the amplitude. If your amplitude is at 2, you can't reduce it to 1.5. You have to go straight from 2 to 1. And what that means is you're actually talking now about individual photons or individual particles of light. So does that clarify a little bit how we can talk about light as both a particle and a wave?
Okay,
So-
wait. I think
So I think that's sort of jumping the gun a little bit.
Yeah, I think
we don't know what the result of this experiment is yet, actually.
Yeah, that's
Okay.
true. But
Okay, so I think I'll just continue. I hope if people are confused, please like write in the chat what you're confused about. But I guess for the sake of just continuing on with the lecture, I'll continue. So I said we were sending in one photon at a time, and what you can see in the left, you can kind of see a pretty random distribution. But as you kind of increase the number of trials, you can kind of see a more clear picture. And in fact, what you get, is you get a very, very clear picture of the wave pattern. You get these really clear bands, and you can see that the center is much more defined, and you have these parts which are representative of like the troughs or the parts of deconstructive interference. And so this is really cool in that, and really interesting because we were only kind of putting in one photon at a time, but somehow we were able to produce this wave pattern. And it was almost like as if when we were sending in one photon, it was somehow going through both, interfering with itself in order for it to kind of produce this wave pattern. And keep in mind, it's not that one single photon is making this spread. It's one photon is making one dot, but over time, we then get this wave pattern. I hope that's okay. Do people have any questions?
So this is supposed to sound weird because
Yes, like if you are uncomfortable with this, that's good because it should be uncomfortable. Because somehow, even though we are kind of dealing with these particles of light, like one at a time, we're sending them in, all of a sudden we're getting like, albeit over multiple trial or like multiple kind of processes, we're getting this wave pattern. And so scientists kind of, I was mentioning how it almost seemed like as if the photons were going through both slits at the same time and then interfering with itself. And so what scientists figured out is like, why don't we put a detector on both of the slits to see whether or not we really are getting somehow two photons going through each of the slits. And so when this happened, they noticed that they only got instances where only one of the detectors were set off. So it was like one photon was only going through one of the slits. However, when this happened, when people were putting these detectors on the slits, all of a sudden the pattern produced on the screen was that of the particle pattern, was that of the global distribution that we saw with the bullets. So somehow, when we've had the detectors there, kind of confirming that there was only one particle going through one slit, the pattern on the other side changed.
So also, like after this first experiment shows that you can see like a diffraction pattern on the screen, what you should be thinking is, well, if I'm a photon and I'm going through one of the two slits, how do I decide which path to deviate and like where to end up on the screen, right? If it's just a single photon that you're talking about, the path should be like straightforward, and you should just get the two bands. When you're talking about this diffraction pattern, like the question naturally arises, like, what is the path that the photon is taking through the slit? And so that's what putting a detector to actually see the photon going through the two slits. That's why you want to have that detector there to try to investigate what's going on.
Yeah, but sense? Yeah, and somehow by detecting which slit the photon was going in, somehow the pattern was changing. So this was really crazy because it's almost as if the photon is like sentient and it knows what you're doing and it's reacting to what you're doing. And so scientists are like, okay, let's take away these detectors and let's do a different thing. What if we send in a photon through the slits, and then after the photon has passed the slits, we close up one of the slits, so then it becomes like a single slit experiment. Weirdly enough, so there's no detectors, but however, when this happened, the pattern changed again from a wave pattern to a particle pattern, to kind of just the bands, or the kind of the bell curve distribution. And so what this also implied is all of a sudden it seems like even though the particle had already passed the slits, the second you close up the slit, it's like as if the particle as if the photon knew that, oh, behind me the slit is closed, so I can't necessarily interfere with myself, and so I'm going to act like a particle now. Basically the gist is, when we interact with the experiment in different ways, we kind of get these instantaneous changes of whether or not light is behaving like a particle or like a wave. Okay, Shashank sent a relevant meme. Somebody said, I guess probability sounds better as an explanation. We'll address that later. So this is pretty crazy, and I hope that this is starting to feel weird for you guys, because somehow the photon knows whether or not you're looking at it and you're investigating whether or not it's a particle or a wave, and it's changing like based off of that. And the implications of this are really interesting, because then if you have a screen, if you're conducting a double slit experiment and you have a screen that's very, very far away, like you can even say light years far away, and you send photons through the slit, and then as the photons are traveling towards the screen, which is very far away, you then instantaneously, or then you then cover one of the slits, you can then instantaneously kind of change what the pattern is going to be on the screen, which is pretty crazy. So yeah. Basically,
I guess one other thing I want to say, which makes it sound very strange, is if you only have one slit, it doesn't really matter if it's a particle or a wave. You basically have like a big peak in the center. But somehow when you open up another slit, there are points where like fewer photons hit, which doesn't make any sense, because you would think that that could only increase the number of photons that hit everywhere. but actually somehow like because of interference, like that brightness at certain locations actually decreases, even though you're like letting more light in, which is super weird.
Mm-hmm. Yeah, that kind of comes up with that like wave property with like the constructive and deconstructive interference. And so scientists were really boggled with this because all of a sudden there was this like weird like juggling between like light as a particle, light as a wave, light as a particle, light as a wave. And a lot of scientists were thinking maybe light is something that's just really unique in this like sense, in that it has kind of this duality to it. However, scientists in 1927, 3 scientists did the same double slit experiment, not with photons, but with electrons. And what do you guys think the pattern is going to be? Because clearly, okay, photons, we've kind of argued that it's a particle, but they're kind of hazy. But I feel like with electrons, in our minds, it's very clear that electrons are particles. Electrons are like things that we can see, like they have a place and a position. And they're very different from this concept of waves that, like when I think of waves, I think of ripples on the top of water. Like they're very different, right? So what do you guys think? Do you guys think with electrons and a double slit experiment, do you think we'll get a wave pattern or a particle pattern? You were taught in AP Chem that electrons had wave-like properties. Yes, wave, okay. So it seems like people kind of have learned the answer to this question. And it's that when you do it with electrons, you also get this wave pattern. Here's a picture of electrons being shot through a double slit experiment, and you also kind of get these bands. And this has been done not only with electrons, but also with atoms, with whole molecules, which are tens of thousands larger than protons. So we can definitively say that this is not just a property that's like seen only with light. This is definitely something that we see both with light and with matter as we know it. And so what's going on? This is in quantum mechanics what we call this wave-particle duality. And this is the idea that everything can behave both like a particle, interesting, both as a particle and a wave. And so wave properties can then be described by a wavelength. And this is called a de Broglie wavelength after the person de Broglie who kind of came up with this idea of wave-particle duality. And so this wavelength is equal to h, which is Planck's constant, which I mentioned before, and it's divided by the momentum of whatever we're talking about. And so this was really groundbreaking because obviously you and I are not waves. Like obviously we are just like physical kind of things, and we're made up of atoms, which we kind of associate, which we think of as particles. However, we can still kind of characterize our own intrinsic wave properties with this wavelength. And so even for us, we have our own de Broglie wavelength. The only reason why we don't really kind of feel or experience things, everyday objects, as waves is because their wavelength is really, really tiny. And the example is that if I, like a kind of human being, was running at 10 miles per hour, and I tried to calculate my wavelength, it would be 10 to the negative 34 inches, which is very, very small. And so as you can see, it's 1 billion, billion, billion times smaller than an atom. So it's basically negligible, and you can't really interact with me as a wave. But with things smaller like atoms and electrons, you can have a de Broglie wavelength that is big enough to interact with on that smaller scale. And I think that's the key here that we'll see of quantum mechanics is in this here in our macroscopic world, our world is governed by Newtonian mechanics or classical mechanics. But as we go into this smaller microscopic world, we start getting weird things that seem very unintuitive in our understanding of the world. But in that smaller scale, things that we don't really think about or really have to care about in our macroscopic world kind of manifest. And we see that. And one of those big examples is kind of this wavelength. So, does anybody have any questions?
Can I ask a thought experiment as well?
Okay, yeah.
What do you guys think would happen if you were doing the double slit experiment with electrons? So you were like letting them through, but you would like measure like which slit the electron would go through. So you sort of park like a detector at one of them and check if it's going through. What's the same thing as the photon experiment? What happens? Yep, that's right. It would act as a particle. And so it actually somehow knows that you've measured it. That's kind of weird.
It's pretty spooky. Yeah, there's a lot of things in quantum mechanics that are pretty spooky. But if there are no immediate questions, I'll move on. So we've basically established that kind of the things we deal with all kind of have this wave property and particle property. And so in the past in Newtonian mechanics, we've had these kind of models for both, and they've been quite distinct from each other, but now we kind of need this new this new concept to describe things that exhibit both wave and particle properties. And so how do we describe something that's both a wave and a particle? We use something called a wave function in physics, and this is essentially just a mathematical description that tells us the probability of finding something somewhere. And this comes from the square of this quantity. And so what this is, before we talk about kind of delving deeper into what the wave function is, I want to talk about a really important equation in quantum mechanics, which is the Schrodinger's equation. And this equation essentially gives us our description of what the wave functions do in a certain quantum system. And so just like how in classical mechanics, we use F equals ma, and this equation then gives us kind of the relevant equations of motions. Like from this equation, we can derive the energy of our system, or we can describe like the acceleration or velocity of our particle. We can do the same thing with wave functions and Schrodinger's equation. So this is kind of its form in full generality, and it seems pretty complicated because there's like a lot of fancy symbols, but it's actually not too bad if we dissect it. So here is the Greek letter psi, and it represents the wave function. And on this left side is essentially something called the Hamiltonian, which is it's an operator which gives us the energy of whatever we're looking for. And so here, this is, maybe you can remember what the symbol is from E&M, and this essentially was just a spatial derivative, and it's of second order because there's a 2. These are constants, and here is potential energy. So it's essentially saying, like, this on its own is kinetic energy, and this is potential energy. It's actually, yeah, actually I have it right here. So yeah, kinetic energy and potential energy. And so you can notice that here we kind of, the right-hand side is like a little different. And it's just that this one is a time-dependent equation for the wave function, and this is a time-independent wave equation for a wave function. So if we look at this equation, which is a time-independent wave function, this is essentially just a statement of conservation of energy. You're saying that if you add up the kinetic energy of your wave function and the potential energy of your wave function, you'll get the total energy of the wave function. So it looks kind of complicated, and if you kind of go into the math, it's complicated. It can get complicated, but essentially it's just a statement of energy conservation, which I'm pretty sure all of us are pretty familiar with. So one important thing about quantum mechanics is that we deal with the probabilities of our wave function. And I mentioned how the wave function squared is how we determine what the probability of where our wave function is, or kind of what state our wave function is in. So this is just an example of showing that the probability kind of if you like to think of just like how we kind of had those bell curves with the distribution of the bullets, these kind of graphs are just essentially showing us where it's likely for us to find our particle where. And so you can use kind of these similar graphical representations to deter, like just like how we did with the double slit, this is the same thing. It's perfectly analogous.
And so like Yonna said, the wave function is like a thing that like describes the probability of stuff happening. So you might remember that at some length in the review last week, we talked about determinism and how we basically assume that the entire time. But there isn't any determinism here.
Mm-hmm. I'll go into that. But yeah, so now we can just talk about wave functions. And so on the right here, what we have is a wave function describing what a particle is. And so we have a delta function. And essentially what a delta function is just a way to kind of show like what it is that there's a big spike at x equals 0, which is like this line right here, and everywhere else is 0. So it's very clear and very defined where the position of our wave function is. It is right here at x equals 0. On the contrary, if I were to ask you where the position of this wave function is, which is very much like a wave, it's a lot harder to answer that seemingly simple question of like, where is the wave function? Because in fact, this wave is, in a way, it's kind of, you know, propagating everywhere. However, it's quite easy to kind of determine what the like velocity or the momentum of this wave function is. You can determine by like its speed or its wavelength. And so in that way, describing a wave function for a wave is a lot easier. But one thing you've noticed is that there's kind of this trade-off when you were talking about waves and particles. There's kind of this trade-off between position, which is like very well defined for a particle, but not so easily defined for a wave, and then vice versa with the momentum, where for a wave, it's very easy to kind of determine kind of the speed and direction a wave is traveling at, versus for a particle, it's harder to do that for a particle. And so you can kind of do a compromise and have something called a wave packet. And so here you can kind of see that, okay, there kind of is a relatively defined position of this wave packet. And you can also see that it's composed of these smaller waves. And so here it's easier to give it a position and a momentum, but they're still both not defined. And this kind of leads to a really important concept in quantum mechanics, which is this concept of uncertainty. And Heisenberg's uncertainty principle tells us that for a wave function, you can know either the position or momentum, but not both with full certainty. So there is a certain trade-off, and there's a minimum amount of kind of uncertainty that is associated. Like that's just intrinsic and natural. And so this might seem kind of weird because in everyday life, you kind of look at something. So if I have like my phone here, well, it's very clearly in my hand and I'm moving my phone. Okay, well, it's very, like I can then very well define what its momentum is, like both at the same time. So it's, in real life, it kind of seems weird that there is this sense of uncertainty. However, this is because if you look at the actual value of this uncertainty that we're describing, so this h bar here is Planck's constant h divided by 2 pi. So I mentioned earlier that h is a value that's something like 6 times 10 to the negative 34. So it's incredibly small, this uncertainty. But when you, like I said before, when you are at that small scale of particles, then that uncertainty does manifest, and you can see it when it comes to kind of defining these wave functions. So I've talked about wave functions, and one thing we can do is now kind of look at our model for the hydrogen atom. And so in the early 1900s, Niels Bohr, who is a famous physicist, was looking at the model of an atom at the time. And then the accepted model was that of an electron orbiting around the proton. However, this kind of had a big flaw because classical mechanics tells us that the kind of attraction between the negative electron and the positive proton would make it so that the electron would then very kind of quickly spiral into the center. However, we know that that's not the case. The electron is very much just orbiting around the proton and not spiraling. And we also observed that when heated, the hydrogen emitted only certain colors. Here you can see this kind of spectrum. And I think this was like even described in astrophysics lecture where you have these like really unique bands that you can see, and they're kind of intrinsic to hydrogen as an element. And so these bands are really specific and they're very certain. And so it kind of implied that electrons had a certain energy or quantized energy. And so to kind of explain this with quantum mechanics, we want to look at something which is kind of analogous, which is the particle in a box model. And so we've talked about wave functions and how they kind of, we can represent them with these like wiggly lines, for example, or these waves. However, if you kind of confine a wave function in a box per se, and so here you can see these like walls, then we kind of are confining our wave function to this certain space, and we're imposing boundary conditions at positions like x equals 0 and x equals L. And so at those points, we have to have the wave function kind of die down to 0. If you want to think of an analogy, if you have like two people holding a piece of string and you kind of both shake the string on both ends, this kind of string is going to be kind of wiggling and going around all crazy, but at the 2 points where the people are holding the string, they're fixed. They're not wiggling. They're kind of essentially, you can define those to be 0. And so in the same way, when you have a particle in a box, you're imposing what the wave function can be. And so when you do that, as I kind of mentioned earlier with Schrodinger's equation, the wave function is very closely related to the energy. So when you're imposing a restriction on the wave function, you're then imposing a restriction on the energies. And so in this case, you can get kind of quantized energy in this bound state. And so with this, you get kind of a minimum energy. And so what you can see here is kind of the simplest form where you just have one kind of clean arc from one end to another. And so this is not a perfect, I guess, like representation of what's going on with the hydrogen atom, but kind of generally what you can say that the electron is bound to kind of this orbit around the proton, and that this bound, the electron being bound to the proton is kind of analogous to the wave function bound to the walls of the box. And so here you can also see that this is kind of the hydrogen atom's energy levels. And here you can kind of see it's similar in a way. I mean, they didn't draw out the explicit like wave functions, but there is this minimum energy that the electron has. And because of that minimum energy, we get that the wave, or the electron doesn't just kind of simply spiral into the proton, because it has this minimum energy that it has to maintain its position rotating or orbiting around the proton. And the key point here is that energies are quantized, but they're only quantized if the wave function is in this bound state. And what I mean by that is if the wave function has enough energy to kind of overcome this boundary, then it can very well be continuous. And so want to ask you guys a quick question. And this is not a trick question, but let's say we had some ping pong balls in a box. How do we get the ping pong balls out of the box? This is not a trick question.
Take them out.
Okay, maybe yes, take them out. In what way? Flip the box over. Okay, that's big brain. I did not even, that was not, break the box. Okay, wow. Okay, assuming we can't touch the box and you can only touch the ping pong balls. Somebody said take them out. Yes, that's the answer, I guess, just for the sake of moving on. But simply what you do is you grab the ping pong ball, you impart it gravitational potential energy enough so that it can overcome the boundaries of the box and kind of move out, right? And that's kind of the classical answer. There's only one way for the balls to kind of get out of the box. That's you give it enough energy so that it can kind of hop over this energy kind of barrier. However, in quantum mechanics, as you can clearly see, quantum mechanics seems to just, be different from in any way that you expect it to be in classical mechanics. In quantum mechanics, there's this concept that things can go through barriers. And how is this possible? Well, wave functions I mentioned are this kind of probabilistic explanation or they're kind of this probabilistic representation for like particles or waves. And so there is a non-zero probability to find a particle on the other side of a barrier. And the energy of that wave function will be the same. It's just that the probability of finding that wave function on the other side is greatly decreased. So this might seem weird or like, okay, this doesn't make any sense, but what this essentially is saying is that a wave function is a probability distribution. And so just because you have as long as that barrier is not an infinite potential, there is some probability that can leak through an energy barrier and kind of exist on the other side. And this can very much mean that we as people, because we can also be represented as wave functions, if we were to, there is a non-zero probability that we can, if you run into a wall, there is a non-zero probability that we could somehow make it to the other side of the wall. Are those probabilities high? No, they're very small. In fact, it's the probability of somebody successfully tunneling through a wall is on the order of 10 to the 10 to the 37th power. So that's like 2 exponents. So it's incredibly tiny, or like the probability is incredibly tiny. But like I said, for smaller objects in that microscopic scale, this is very, very well like observed and like, I don't want to say common, but it is possible and observable at those small scales. So I want to talk about just check the time. Okay, so I want to talk about one more quantum phenomena, but before I do that, I need to explain a concept called spin. And so spin is an intrinsic property of matter. When we say spin, we're not talking about particles. We're not saying that particles are literally spinning, but it's just a word we use in quantum mechanics, and it's basically equivalent to an intrinsic angular momentum. And so what this is in classical mechanics, when you kind of think about a charged spinning object, we know from classical E&M that this charged spinning object is deflected from a magnetic field in a way that's proportional to how fast it's spinning. However, with the spin that we're talking about here in quantum mechanics, this is not necessarily the case. And in 1922, 2 physicists, Otto Stern and Walter Gerlach, showed that if you send a stream of electrons through a magnetic field, this would effectively then split into 2 separate beams, which are perpendicular to the direction of the magnetic field. And so classically, you would expect this to be more of like a continuous spray. However, this kind of showed that electrons don't have this kind of like range of angular momentum, but instead have 2 very discrete types of spin, like spin up or spin down. And for electrons, we define it to be a half integer spin. And this is important because it turns out that this property of spin is intrinsic to kind of all particles, and we are able to divide or like kind of group particles based off of what type of spin they have. And so electrons have half integer spin, so they are in a group called fermions. And fermions are in general, they describe particles that have half integer spin, so that's like 1/2, 3/2, 5/2, etc. And there is this really important principle called the Pauli exclusion principle for fermions. And what this essentially says is that two fermions cannot exist in the same state unless they have opposite spins. And so maybe you've seen this in like a chemistry class, because this is really important in chemistry. But essentially what that's saying is that for each kind of state, you can only have up to 2 electrons, one spin up and one spin down in that state. And so this is important for the next concept that I'm going to talk about, which is quantum entanglement. And so before I go into kind of the quantum mechanics, I'm going to kind of give an analogy that's a lot more simple to understand. And so here, for example, we have 2 people. Let's just say it's Stern and Gerlach from the Stern-Gerlach experiment. And let's say that it's wintertime and they both need gloves for the winter. So they both go shopping together, and it turns out that combined, they only have enough money for 1 pair of gloves. So they reason, okay, well, at least 1 glove is better than no glove. So they agree to buy like 1 pair of gloves, and then to divide, and like each person gets 1 of the 2 gloves. However, it turns out that both of them are left-handed, and they're both arguing, and they both want the left-handed glove. And what happens is, okay, well, they have 1 left and 1 right. Why don't they do this? They'll put they'll put each glove in a box, and they'll kind of jumble up the box so they don't know which glove is in which box, and they'll just arbitrarily choose one of the boxes, and they'll go home and they'll open up, and whatever glove they get, they get. So that's what they do. So they go home, and let's say we're following Stern's perspective. So he goes home, he opens his box, and voila, he has a left-handed glove. And we don't know what Gerlach's doing, but in that instant, when Stern opened his box, we know immediately that Gerlach then must have the right-handed glove. That makes sense, right? That seems pretty trivial, but it can get a bit more complicated when we think about it, the consequences of something like this in quantum mechanics. And before we do that, I want to talk about something that many of you might have heard of. Oh yeah, so here, sorry, before I do that, I guess I should just reiterate. So in quantum mechanics, we can kind of do a similar scenario where we have a spinless particle. And so a spinless particle is essentially 1 of 0. And we can have this particle to decay into 2 different particles. And by conservation of angular momentum, we know that the total spin of these 2 particles must equal 0. And so if that was the case, if we were to measure one of the particles to be spin up, for example, then without knowing what the other particle is, we must instantly know that the particle must be spin down. And so we say that these 2 particles are entangled. So like I said, this seems pretty analogous to the glove story, and it doesn't seem too crazy. Before I move on, does anybody have any questions about what I mean by entangled? Okay, if not, I'll move on. Okay, so we're going to talk about, like I said, something that's kind of maybe most, if not all, have heard about, which is this concept of Schrodinger's cat. So to kind of explain what this thought experiment is, this was a thought experiment from Schrodinger, who created Schrodinger's equation. And he essentially said, if we had a cat in a sealed chamber and then we left the cat in that chamber for 1 hour with this device, and this device has this radioactive material, which we know in 1 hour has a 50% chance of decaying. And so if this material were to decay, then it would hit a counter, like a detector, and that detector would then it would then be programmed to take a hammer and break open a vial of cyanide, effectively killing the cat. Cyanide is a poison, if you didn't know. So that's 50% of the chance, and there's 50% chance that the radioactive material won't decay and nothing will happen and the cat will live. So effectively, there's a 50% chance that the cat is alive and a 50% chance that the cat is dead. And so after an hour, you go to the chamber, and right before you open the chamber, in quantum mechanics, you would say that the cat is in a superposition of being both alive and both dead. And that might seem weird and unphysical, because it is. You can't really think of what it means to be both dead and alive at the same time, but that is how quantum mechanics deals with this general kind of like uncertainty in what a state is before you measure it. And so the importance of this thought experiment is to the point to take away from this thought experiment is to kind of think about what it means to measure a system. Because in quantum mechanics, what we say is that this cat is in the superposition of both being in a state of being alive and also being in a state of being dead. And so only when we open the chamber and see for ourselves whether the cat is alive or not, the act of us opening and kind of observing the cat is what we call collapses the wave function, and then we can see whether or not the cat is dead or alive. So in some ways, you can say that it really is the act of us opening the chamber which kills a cat or not. And so in quantum mechanics, we kind of have this concept of it's the measurement that kind of determines the reality of what's there. So before we observe a state, it's almost meaningless to kind of like to even ask the question of what the state was like before we observe it. Because if you think about the wave function, there's all these like probable kind of states in which we can see in which like kind of the state could be in. It's only when we actually measure it, whether that's like opening the chamber and seeing whether the cat is dead or alive, or in the case of like the double slit experiment, where we kind of measure what slit the photon is going into. It's only the act of measuring do we really see what the reality is of our state. I hope that makes sense. I see there is something in the chat. When you go to the bathroom and come back to, okay, yeah, sorry. So if I don't open Gradescope after finals, I can't be judged. That's true, but I guess in that sense, though, the person who, like, there is somebody who in a way has determined what your final grade is, so it is already determined? Okay, I'm sorry.
Yeah, there's a paradox called Wigner's friend, which you should look up, which is a very philosophical philosophically big deal in quantum mechanics.
Yeah, and there's a lot of philosophical debates that derive from quantum mechanics because it really asks us to, like, what is it? What is a measurement? Like, defining what a measurement is not answered. Like, we say that the measurement is what determines what the state is, but it's kind of arbitrary. We haven't yet really fully defined the parameters of what a measurement is. Anyway, so kind of going back to quantum entanglement. So there is something called EPR paradox, and this was a paper written by 3 people. Unfortunately, I don't know who the P and R stands for, but I do know. Do you know, Nicholas?
It's Podolsky and Rosen.
Yes, but E is Einstein, so I do feel kind of bad. Podolsky and Rosen. And so in this paper, Einstein was kind of talking about the more like philosophical implications of quantum mechanics with this concept of entanglement. And in this paper, he called entanglement the spooky action at a distance. Because in quantum mechanics, we've claimed that the measurement is kind of what gives us the reality. But Einstein was claiming that, okay, then with entanglement, because if we had, like I was mentioning kind of the 2 particles, whether or not, like, we don't know what the spins are, but if we were to put them far away and then measure what the spin was, in a way, yeah, so if we put them far away and we were to measure what the spin of one of them was, that would instantly then enforce what the spin of the other particle would be. And Einstein was claiming that, that kind of passing of knowledge of what spin or what state the particle should be in, that information then must travel at a speed faster than the speed of light, which would break relativity, because as we know from special relativity, nothing should be traveling faster than the speed of light. And so Einstein in this paper proposed that there must be some other hidden variable, and that our understanding of quantum mechanics is incomplete. And so for decades, this was kind of like tossed around, like people were trying to figure out what this hidden variable was. However, I believe in the mid-60s, 1960s, John Bell kind of came up with this test to figure out whether or not there was a hidden variable needed. And there is kind of a long process of explaining what this test is, but essentially it kind of using this inequality, this mathematical statement called the Bell's inequality, it essentially showed that there is no hidden variable, and it's not the work of quantum entanglement is not the work of some other hidden variable, but we can properly describe what's going on with quantum mechanics, with the quantum mechanics that we know. I do suggest, if you want to learn more about the process or this test that John Bell made up, there is a Veritasium video on it. So that kind of explains in detail what the test was and how he proved, John Bell himself didn't do the experiment, other scientists after him conducted it, but through this test, we were able to show that quantum mechanics, as of right now, is complete, and it is able to properly explain what quantum entanglement is.
We will discuss it a little bit more next time as well.
So overall, I think there's kind of a lot of these general kind of philosophical questions that quantum mechanics brings up, and there's a lot of questions about interpreting quantum mechanics and how we kind of perceive reality, because quantum mechanics basically tells us, or basically there is this big question, like, what's going on? Why is it that, when we measure something, it turns out this way, but then when we measure it another way, it somehow it seems like as if the state knows that we're measuring it, so then it moves another way. There's a lot of looming questions. And so the kind of general consensus that I've been describing with this kind of use of measurements is known as kind of the orthodox or generally accepted view of quantum mechanics, or the Copenhagen interpretation, which was very kind of strongly associated and supported by Niels Bohr, who's a famous physicist in the 20th century. And so kind of like what I was saying earlier, this kind of understanding or interpretation of quantum mechanics says that it's useless to even think about or to even try to formulate a sense of reality of what reality is before we make a measurement. In fact, it's the act of making a measurement of what our world is. That's what's forming our reality. And so measurement is just simply picking out one possible state out of all the possibilities described in our wave function. And through that, we're collapsing our wave function. And that is kind of the philosophical interpretation of quantum mechanics. However, like I said before, there are kind of subtleties in kind of defining what exactly it means to measure something, whether it has to be, there are lots of interpretations, whether that some scientists kind of figure that there's some kind of like connection with the human consciousness, that like somehow the human consciousness is what, like when you interact with something with your consciousness, that's like what it means to be measured. Or some other famous scientists think that it's more about the like the final cause, or the final like state that you see it in, and whether like it's irreversible or not. Like there's many interpretations essentially kind of adding on to this interpretation. There's another kind of general interpretation that's called the many worlds interpretation. And here, the people, or proposed by Hugh Everett, he proposed that we shouldn't think of quantum mechanics as a collapse in the wave function. And in fact, every quantum measurement, every like possibility that we have for every wave function kind of splits, and that all of these possibilities are carried out, maybe not necessarily in our world, but in kind of another variation in the world. And so you can kind of think of all the possibilities splitting into all of these multiple branches. And when we measure something, it's not about collapsing a wave function, but more in that we're like entangling ourselves with the state. And so in that sense, you can kind of think of the world as one really large wave function that kind of collectively has all the details of every single like quantum measurement that we have. And so that's kind of the end of what I have. Here are some of the key points that we've brushed over. We've gone through a lot. We've started off with this understanding of this particle wave duality, and that everything can act both like a particle and like a wave. We have this uncertainty in measurements, and that there is an intrinsic uncertainty when it comes to making measurements in a microscopic level. Energy is not continuous like we understand it in the classical world, but it's actually quantized. And there are certain phenomena like tunneling and entanglement. There's questions about measurements in quantum mechanics, and ultimately these kind of end off with a more philosophical interpretation. We have 5 minutes left, and I think this might be a good time for people to generally ask questions that they have, because this was a lot of kind of new topics, and I hope it wasn't too much. I hope it wasn't too confusing. Yeah. Does anybody have questions? I think one good thing to note here is that I've kind of brushed over, like a lot of this is math, and so it kind of might seem random in that I'm just kind of throwing certain things, but there is math to back this up. And in fact, quantum mechanics, it started in the early 1900s And since then, it's really been refined and reformed. And the beauty of quantum mechanics is that it's purely a branch of physics that kind of works to confirm what we observe, in that we really have no idea why things are like this, but we've somehow managed to figure out certain sets of mathematical equations that have like a really strong predictability, or like predicting powers when it comes to those microscopic systems. And it's worked so far for us. Yeah. Do you know what the Yelkia? Yeah. Okay, it seems like nobody has questions. We can finish 3 minutes early. Nicholas, Shishir, Shashank, do you guys have anything you want to add last minute?
That's it.
I guess the big picture like idea is that you can sort of try and think about these counterintuitive ideas in terms of waves. So like all of these concepts that Yonna was talking about, like can be understood from the perspective of waves.
Yeah, I agree with that. I think a lot of the weirdness of quantum mechanics comes out of just a couple of things that if you like if you sort of understand those few things, then like you can sort of all of the weirdness of quantum mechanics comes out of that. So, and one of those is that you treat things as waves.
I would go as far as to say that if you wanted to go and like learn quantum mechanics, you wouldn't have to learn normal mechanics before doing that, because it's just so different.
Yeah.
Mm-hmm.
I feel like a lot of people, like, I don't know if people were like not just asking questions, but I feel like people took it really well. I don't know.
What do you mean by took it?
Would you like to stop the recording?
Oh, yeah. Haha, how do I do that?
You should be able to just press the same button again.
Yeah, stop recording.